And the final speaker of the session, it's remote again. We have Jean-Philippe Beaulieu from University of Tasmania and IAP.
Good morning. Good. Okay, so sorry for not being with you this time, but I'm going to be with you remotely. I give this talk on behalf of a group of people who are part of the Euclid exoplanet working group. And we're going to discuss what we can do with actually Euclid observations of the Roman field. So this is actually a long story because microlensing of exoplanets has been part of the Euclid science case in additional science since the beginning. And there have been various contributions, in particular for Raymond Kerings, Matthew Penny, Etienne Bachelet, and all the people who are listed here. So I'm giving this talk on the behalf of all our group. As you know, Euclid launched about a year ago, and at Capricorn. So Euclid is a European Space Agency mission, so it's much smaller than Roman. It is a 1.2 meter telescope with two instruments. And I'm just going to just give you the highlights of the instrument so that you see what are the performance. So first there is what we call the VIS channel, which is 0.57 square degrees covered with teledyne detectors. And the CC is giving you a fully detached max of 0.18 arc seconds, which is actually well matched with Roman. And then there is also an instrument which is called the NISP, that is taking observations in the infrared in the Y, J, and H band. Here, the pixel scale is much larger, 0.3 arc second. Note that for the channel in the visible, we have one single band which is broader than the usual. So here you have the transmission. So I leave these slides for references so that if later you wonder what are actually the performance of Euclid, then you can have this available. So you see it is basically going from 0.55 to 0.9 micron for the VIS, and then in the infrared, these are the standard bands. Since Euclid launch, so there have been some issues. So let's just recap on them so that this way you will know where we are. So shortly after launch, there was a problem with the fine guiding sensor, which was something based problem of the prime contractor. And so this has been fixed. There is also some stray light coming into the VIS instrument. This has been, so it's basically light reflections of one of the thruster, and then the light finds its way in the instrument. So this has been mitigated by actually changing the observing strategy of the telescope. Normally what you do is that you have the sun, which is kept at 90 degrees of your telescope, so basically you are in the shade. And so there was an operating angle going from -7 degrees to +7 degrees. So basically your telescope was able to move by -7 + 2.7 and then observe a long circle. So because of the new straight problem, then it has changed actually the range of pointing angle, and which is now between -8.5 to -2.9. So somehow it is creating an asymmetric scan of the sky, which is a bit more complicated in terms of scheduling. So it means to perform the surveys for cosmology, then they will need some slightly more time. Of course, you know that there is the high solar activity these days, is higher than expected. And there's been a bit of icing on the instrument, but this is basically taken care of by doing some defrosting, and then you just regain the loss in throughput. So basically now things are on track. We need slightly more time, and the survey is ongoing. So the survey is ongoing, meaning for the cosmology part. One thing to keep in, also to be precise, to keep in mind is Euclid is observing with fixed observing sequence. We call the reference observing sequence, so ROS. At each positions, you have 4D there with 285 seconds exposures in the VIS and 54 seconds also in the VIS. And then you have short exposures taken in a NISP in Y, J, and H. And one ROS is basically a combination of these different observations. So there is no way for us to change this observing time. So if they, oh, I just would like to have twice or half the observing time, no. We have to basically stick to it. That means any observations that we should do with Euclid will have to be done with this particular setup. And as a teaser, I said that our standard observations, if we do microsensing observations with Roman, would be to basically do 4 rows at each these positions for the precursor survey. Okay, you know the Roman fields. So this is based on the work from Matthew Penny. So there are 2 realizations: the reference survey with 7 pointing in black, and then an optimized survey plotted in light blue, and then another one which is for beta would be for mass measurements, which is plotted in green on this. So you see this figure that has been probably shown already. So the idea would be to try to cover this with Euclid. So if we want to match all these observations, all the different realizations of the Roman fields, or most of the realizations of the Roman fields, we can just do it using 9 pointings of Euclid. So by doing 4.5 square degrees of the galactic bulge, you cover most of the Roman fields. And you can say, well, yeah, but ultimately Roman will probably do only 2 square degrees, but having this wide survey of Euclid is actually the best good way to try to refine what will be the final fields to be observed by Roman. So why we would do these kind of observations, to do observations of this of the Roman fields. So first, it is helping to try to help to optimize the Roman position. There is something else that is actually very interesting, and which is actually the first one I would put on the list, is that if we have one epoch with Euclid slightly before the Roman field, the Roman microsensing survey, then it means it is giving a constraints for relative source length proper motion, because few years apart, source and length will be slightly separated, and then we can constrain the relative separations between the two, which then will go into the modeling for constraining the mass of the system. So it means by having one snapshot observations with Euclid early on, then we can basically give constraints for mass measurements. And this is from the year 1 of Roman. Of course, by design of the requirement of Roman, when you combine all the Roman seasons over 5 years, then you will be able to use Roman observations alone to do the mass measurements. But having Euclid observations means that you get the mass measurements from year 1. Yeah, just pass this. So Etienne and Matthew actually discussed what would be the best observing strategy in terms of exposure time. So we thought, and it is published in Bachelet 2022, that the best choice is actually not to just take 1 Euclid observations, but 4 Euclid observations at each these positions to be able to reach the C9 to noise ratio that will help us to well constrain the source and lenses. The reason we want to do that for the mass measurement is basically perfectly exemplified here with this paper that was the study that was done by Aparna Bhattacharya and us in 2018. So here you see a system. So this is observed by Keck and HST. So you have observations in the infrared and in the visible. You see an elongation of the PSF, which is due to the fact that you have source and lens were basically slightly resolved. And when you use these constraints on source and lens, which translate immediately into a constraints for relative source and proper motions, when you plug it in
3
for the
minutes.
model, then you get good constraints on the physical parameter of the system. So here you see, as an example, the probability density distributions before the angular resolution constraints in blue. And once you have the constraints coming from high angular resolutions, it goes to red. So typically, you can get mass measurements to 10% if you have these kind of observations. The thing is that we are doing it for years by doing pointed observations, one after the other. Here, by having Euclid observing all the Raman fields, you can just do it routinely for any single objects from the field. So this is just an example of elongated PSF between Raman and Euclid between the two epochs. So keep in mind that we can get precise mass measurements for a large fraction of the sample from the first year of Raman. The last bit I want to mention is free-floating planets. So that's something that is in consideration for Euclid, is that if we do simultaneous Euclid-Raman observations of some of the Raman fields, 2028, 2029, then we would get simultaneous observations of free-floating planets, both from Euclid and Raman, and then you will have parallax measurements that will give us the mass of the objects. Moreover, variable stars do not have parallax signals, so that's also a way to discriminate between free-floating planets and flare stars. So the thing we're advocating for is this 4.5 square degrees in the galactic bulge made by Euclid. So this actually has been as a strong support of ESA, the Euclid board, and the Raman pit. We are currently actually in the implementation phase of the survey. The observations will likely be done in March 2025. Originally, they were due to be done at the end of the performance verification phase of Euclid in October 2023, but because of all the problems that they had at the time, all these planned observations from the PV phase were cancelled. So it will most likely be done in March 2025. And then just stress that the simultaneous observations of Euclid and Raman, which is just potential, it is not granted yet, would be a very powerful way to address the questions of free-floating planets. Thank you.
All right, maybe one quick question before the coffee break. Anyone on Zoom or Slack? No? I think everyone's ready for coffee. All right, let's thank Jean-Philippe and the rest of the speakers of this session.